All right, good morning. Let's just do a quick review. What we have been doing. We've been talking about Newton's laws and solving systems of equations involving Newton's laws. We could be solving for acceleration, or if we know the acceleration, then we might be solving for some unknown force like the tension or the friction or something along those lines. But basically, the process is the same. We draw a picture, we make sure we get all the forces in the picture, and that's really the heart of it. If you don't get that stuff right, you cannot do these problems. Once we have all the forces drawn in, we kind of have to make a decision about where the x and y axes live. So for example, if we have an inclined plane, we may want to tilt the axes a little bit, or tilt the picture so that it lines up with our normal x and y axes. And then we have to find components of all the forces so that we can solve separately the sum of the forces in the x and sum of the forces in the y direction. So that's kind of just a quick reminder where we are, what we're doing, and let's go ahead and get started. So I'm going to start with a problem with a pulley because those can be tricky, and I want to reinforce the trick that I taught you last time. So let's imagine we have just a pulley by itself, and then we hang strings on each side of the pulley, and then at the bottom of those strings we have two masses. So we have an M1 over here and an M2. And maybe the M2 is 5 kilograms and the M1 is 10 kilograms. Doesn't really matter what those numbers are, but when I see that the one on the left is heavier than the one on the right, it's more massive, then I kind of know which way things are going to go. And so that's a little bit helpful initially. So I have a picture, and the first step, as usual, is to draw my forces into the picture. So let's use red for the forces. We will have a force of gravity 1 here. That's kind of big because we have 10 kilograms. And here we will have a force of gravity that's about half the size because it's 5 kilograms. Maybe that should be a little longer. Drawing them to scale just helps a little bit. It's not really necessary. Then on each mass, we're going to have tension. So the tension, I know that the tension has to be bigger. It has to be bigger than the force of gravity 2, but so that mass 2 can go up, and it has to be smaller than force of gravity 1 so that mass 1 can go down. So let's try to make this extra visible. And if we label these guys, we have a sense that the tensions should be the same because of Newton's third law. And again, that's true primarily because our pulley doesn't have mass. And in a few chapters, we will learn how to adjust this assumption if the pulley is a heavy pulley. Then it will not be the case that those two tensions are the same. Okay, so those are the forces. I want to make sure I have all the forces, so I check my rule, which is I should have a number of forces equal to the number of points of contact plus 1. So I have only one point of contact on each mass, so I should have 2 forces. Write that better. Should have only 2 forces. So I don't need to do something like put a null force in here. That would be a tendency if I'm just kind of going through the motions without really understanding what I'm doing. So I should instead really think, where's the contact? What kind of contact is it? If it's a rope, that force is going to be called tension. If it's a surface that something is resting on, then that force will be a combination of normal force and friction, potentially. Okay, so now I have my forces, and I am ready to write down Newton's second law. Well, I need to write it down for each mass, because I have two masses. So some of the forces on mass 1 equals m1 times a1, and some of the forces on mass 2 equals m2 times a2. Now here's where my trick for pulleys comes in, because if I don't do something special, then it's going to be the case that mass 2 accelerates in the positive y direction and mass 1 accelerates in the negative y direction, and there's sort of an inconsistency between those two accelerations. And it's not that you can't perform that way, but I think it's a little easier to do the following. To say this mass on the right, mass 2, is going up, and the mass on the left is going down. So I make this kind of bending arrow. I want it to be a little smoother looking. And I just call that the plus direction. I could also call it the minus direction. Doesn't matter what I call it. But I just make a choice that all of the forces that are trying to bring the system in the direction of this arrow, the choice I made is that they get a plus sign. And any force that's trying to bring the system in the opposite direction is going to get a minus sign. Now, once I've made that choice, I can get my component equations, and in this case I only have y components to worry about. So for mass 1, my two forces are T and force of gravity 1. And because I've made this assumption with the blue arrow, I can call both of those accelerations A. So I'm just going to call them both A. On the right, we have tension and force of gravity 2. And I have not put signs in. I want to stress that. That's when I'm doing this, I always just kind of write down what's there, and then I go into the picture and look at the signs. So looking at mass 1, out of these two forces, it's the force of gravity 1 that is trying to bring the system in the direction of the blue arrow. So force of gravity 1 gets the plus sign, and the tension is trying to go the opposite direction, so it gets a minus sign. Then I go to mass 2, and I do the same thing. I say, okay, the tension is the one that is trying to bring it in the direction of the plus sign, so the tension gets a plus sign there. And the force of gravity 2 is trying to bring mass 2 down, which is opposite to my blue arrow. So it gets a minus sign. Okay, so if I got my drawing right, and I use this trick, it should be the case that one equation has T and the other has minus T. So once I'm in that position, I can just line the equations up and add them. And when I add them, we will see the tensions canceling. And that's not special to tension, that's special to Newton's third law. So it wouldn't matter if these were just two blocks that were touching each other, and I'm pushing one, and the one I'm pushing makes contact with the second block and pushes it. There's still going to be an action-reaction pair between those objects, and when I'm combining the equations, those forces should cancel out if I got everything consistently correct. So once I add them, I'm going to have force of gravity 1 minus force of gravity 2 on the left-hand side. And on the right-hand side, I have m1a plus m2a. And I can simplify this a little bit by factoring out the a. And on the left-hand side, m1, force of gravity 1 is just m1 times g, and force of gravity 2 is m2 times g. So I can also simplify this side by factoring out the g. Okay, and then I just do a little bit of algebra, dividing both sides by m1 plus 2, m2. And now I have a formula. And this formula would work anytime I have this situation, but I want to stress, we do not want to memorize formulas. Okay, in fact, if you just whip this formula out on the contest and solve a problem like this without showing how you got this formula, I give you 0 credit. Okay, so this class is not about memorizing formulas. It's about learning basic principles and then how to apply those principles in any circumstances. Okay, so this part at the top is the important part, not the having a formula and plugging numbers in to get an answer. So if I do put my numbers in, I have M1, which is 10, minus M2, which is 5, over 10 plus 5. So that looks like 9.8 divided by 3 if we reduce fractions. And I think that's 3.26 or something, but let me work it out. Yes, 3.27 meters per second. Okay, so any questions so far? Okay, let me point out, just like I did with the previous example with a pulley, and I said I wanted to have a sense of if this answer is right or not. I mean, I get this number 3.27. Does that number make sense? I mean, maybe. I don't think it should fall. I don't think M1 is going to fall as quickly as 9.8 when it's attached to this mass. I know it will be probably somewhere between 0 and 9.8 in the negative direction. Keep in mind, I got a positive sign for acceleration, which means my guess about which way this thing goes is correct. If I had gotten a negative sign, I would still have the right number, but maybe that would mean it's actually going the opposite way to what I expected. So if I have a formula like this and I want to assess if it's correct, again, what we can do is look at special cases. For example, if mass 1 and mass 2 are the same, I would expect this to just balance. And so I should see that in my formula. And indeed, if I put in M1 equals M2, I just get 0 on the top. Okay, if those are the same numbers, I get 0 on top and I get 0 acceleration, which is what I expect. If I don't get that, then I know that this formula is wrong, even though I don't know that much about this situation. Similarly, if M1 is really, really big compared to M2, then we could imagine just crossing out the M2s, and because they're irrelevant. If M1 is very big, if we have 1,000 kilograms minus 1, that's still about 1,000, and 1,000 kilograms plus 1 is still about 1,000. So the M2s become irrelevant, and what I see is that the acceleration should be about g. So if this is a bowling ball and this is a paper clip, then M1 is going to fall with an acceleration about g, and M2 is going to go up with an acceleration about g. On the other hand, if M2 is the bowling ball and M1 is the paper clip, then I would want to cross out M1 as being relevant. And the acceleration I would get would be minus M2 over M2, which is just minus 1 times g. My acceleration would be minus 9.8, which would indicate that the system is going the opposite to my positive direction. But still, this bowling ball would be falling around 9.8 meters per second squared, while this paper clip would be going up around 0 or 9.8, sorry, g, meters per second squared. So anyway, that's just a kind of an idea how if we look at a formula on a test and we're just feeling, I don't know if I feel like I'm not confident I didn't make a mistake, we can check our intuition by making extreme cases. Either the masses are identical or one is very large compared to the other. And you can actually make up numbers to put them into the formula and see what you get and help verify your thinking. And this in particular is very useful logic if you come across a conceptual question. All right, so you have a couple problems that look something like this. And when you do those problems, do not start with this equation, okay? Because if you do, you're really getting nothing out of it. And you will not be able to do that on the contest. So instead, start with the drawing in your forces, writing out Newton's second law, splitting it into components, combining equations to solve for unknowns. If we have done all of this work and we later want to find the tension in the strings to verify what I suggested, that it should be kind of in between this force and that force, we have acceleration now. So we could come right into to this equation, and let me do it in a different color so it doesn't look like our original problem, but we could say T equals force of gravity 2 plus m2a. That's m2g plus m2a, which is m2 times g plus a. And if I put in 5 kilograms and 9.8 plus 3.27, I get about 65 newtons. So some of our problems will want us to do that as well. So we want to see how we can find the tension. And just for comparison, force of gravity 2 would be 49 newtons, and force of gravity 1 would be 98 newtons if we use it. So the tension is kind of right in the middle of those two numbers. Okay, a little closer to force of gravity 2 than it is to force of gravity 1. So it's not splitting the difference, but it's in between them. Any questions about the tension or any other parts? Okay. So let's try a problem from the textbook. We're going to do from college physics, the Shams College Physics book, 3.33. Okay, so take a look at that problem if you have your book with you. It says the coefficient of static friction between a box and the flat bed of a truck is 0.6. So it's the coefficient of static friction is 0.6. Remember, friction doesn't have any coefficient of friction, u, does not have any units. What is the maximum acceleration the truck can have along level ground if the box is not to slide? So we are going to draw a picture. We have the truck. And I'm just going to leave the sides kind of missing so we can watch that box. Okay, I know that's not the best truck, but I don't have a truck, so maybe that's why. Okay, so I want to draw the forces acting on the box. So the truck is moving along, and it has an acceleration, a, which means our box is going to be moving to the right with an acceleration a. Now, if I draw the forces on the box, we are going to have the force of gravity, and we're going to have a normal force, and then we're going to have friction. Now, the friction, which way the friction points, can be a little tricky in this problem. So what you have to do is you have to think, if there's no friction at all, what does the box do? So suppose people in the car, they hit the gas, and this is on ice. There's no friction at all. What's going to happen is the truck is just going to move, and this is not going anywhere. It's just going to stay there. Because there's some friction, the box is going to move with the truck a little bit. So my friction force in this case must be forward. Now that may not be what you were expecting because the box is moving forward. And we tend to be used to friction being opposite to the way something's moving. But keep in mind, you know, a truck only moves forward if it has friction. Okay, if you're ever in the truck and you're on ice and you hit the gas, it doesn't go anywhere if you don't have friction. So the fact that from rest the truck can start moving means the friction is in the forward direction on the tires of the truck. The tires of the truck are moving around in you know, a clockwise fashion, and they're pushing against the ground, and they push the ground backward, and so the ground pushes the wheel forward. So we can have friction that's in the forward direction as well as resisting our motion. So what the friction is doing is keeping the box from sliding off of the back of the truck, which is what is going to happen if there's no friction. Okay, any questions about the direction of friction in this problem? This is a good tip. Anytime you have a force and you're not sure which way it points, you ask, what would happen if that were not there? And that will help you see which way the force must be pointing. Okay, so there we go. We have friction being forward. Are there any other forces on the box that I have to check out? There's one point of contact, so I should have two forces. I have the force of gravity, and remember, normal plus friction together count as additional force because they're technically just pieces of the force of contact between the bed of the truck and the bottom of the box. So this is really all of my forces, and I can now sum the forces. Net force equals MA, which I will have to split into X and Y directions. Maybe I won't need both of them, but now the acceleration of the box is in the X direction, so we're going to have the net force on the box being equal to M times AX. And the only force with an X component is the friction. And the AX is just going to be whatever is the acceleration of the truck. So friction, the question is, what's the maximum acceleration that the truck can have? And so we want the maximum friction that can be found. And remember, the maximum static friction is given by mu static times mole. Okay, well, we want to find A. We know mu, but we don't know the normal force, and we don't know the mass. So this looks bad. Well, we need to first maybe try to find the normal force. And the normal force lives in the y direction, so we go to the y equation. And we have normal force minus force of gravity equals m times ay, but the box does not accelerate in the y direction. So we have, in this case, as I said, this is about 50% of the time true. Normal force equals the force of gravity. And I'll be honest, on this problem, if you've been doing a lot of problems, it will be obvious to you that normal force equals Fg in this case, just as it will be obvious when it's not equal to Fg. So if you assume normal force equals Fg in this problem and you don't show it, I would accept that. I will give you the benefit of the doubt that you came to that conclusion because you understand that it's only true when there's only these two forces adding up to 0, and you kind of conceptually recognize that it works. However, if you make this assumption and it's not true, then it shows me that you really are memorizing stuff instead of understanding, and I'm not looking for memorizing. Memorizing is great in history class, maybe in psychology class, but it's not good in physics class. So I will take a lot of points off if you misuse this. Now, in this case, it's true, and if you thought it was true and use it, I will give you the benefit of the doubt. We have mu static times mg equals ma, and lucky for us, the mass appears on both sides, so it cancels out. And the acceleration then is mu static times g, that's 0.6 times 9.8 meters per second squared, and that's going to be 5.88 meters per second squared. So that's the maximum acceleration the truck can have. If it has any acceleration up to this, the box will go with it. But if it tries, for example, to accelerate at 6 meters per second squared, then what happens is the coefficient of friction turns into mu kinetic, which, just for example, just for sake of argument, it could be something like 0.4. Okay, if it's 0.4, then the acceleration of the box would be only 3.96, I think. Let me try that. 3.92. 3.92 meters per second squared. That's if this acceleration of the truck is 6. The box still accelerates forward. If we're in the truck, we perceive that the box slides backward, but someone outside watching will see the box is moving forward. It's just that the truck is moving forward faster. So the box would actually it would move forward until it fell off of the back of the truck. It would have a velocity that was forward, and it would keep moving forward, and it would bounce a few times. Maybe you've seen that happen on the highway. Something falls out of the truck or something, and when it hits the ground, it bounces a few times and moves forward. It does not just fall straight down and just land and stop, but because the truck is moving forward, it bounces a few times. Okay, so any questions about this problem? Okay. Good. So let's try another problem from the book. This is going to be from the 3,000 Problems book, and it is problem 4.78. So this, I would consider this to be one of the harder problems in the book. Okay, so let me draw the picture, get it set up. We have a tabletop, and there's a pulley on on each end of the table. And then we have a box sitting on the table, and another box here, and another box here. So there's, let's see, there's a rope. There's a rope attached to the box, and then it kind of goes over each pulley. So really two different strings here. And it says there's friction. The coefficient of friction is 0.2, and it doesn't say whether it's moving or not moving. It just says find the acceleration of the system, and to me it implies that they think we're just to assume it's already moving, and so they're indicating this to be kinetic friction. So my hint there, it didn't give us two different values of friction. They didn't give us a coefficient of static and kinetic. If they give us both of those, then we cannot make an assumption. But if the problem just says the coefficient of friction is this, what's the acceleration? It's implying that it's going to move. Okay, and our masses are, we have 9 kilograms here. Let's call that M. They call it C. And then we have MB equals 10 kilograms, and MA equals 6 kilograms. Okay, so that's all of the information that's given in the problem. Now I don't need to look at the problem. I have my nice picture. I would recommend when you're doing homework that you draw the picture over. But of course, you could draw right onto your book since it's a cheap newsprint copy. But I would recommend drawing the picture over like I did, and then you can start to put in your forces. So let's look at MA first. It's going to have only two forces. It's going to be force of gravity and some tension. Okay, and mass C will also have, I'm not going to draw these quite to scale because I don't have enough room probably to do that. And if I label these force of gravity C and force of gravity A, we have here a T, we can call it TA, and we can call this one a TC, perhaps. Then we come up and look at mass B. It is also going to have tension on each side. But because of Newton's third law, I know that the tension on the left should be the same as TA, and the tension on the right should be the same as TC. Now, because the mass on the right is bigger, okay, I am expecting that this object is going to move to the right. So I really should draw TC a little bigger, maybe, than TA. So let's just adjust that a little bit. So make it a little bit bigger. This is not really necessary, but it does help us conceptually to avoid mistakes a little bit. And so the TA should be a little bit smaller than the tension T, or the force of gravity A should be a little smaller than TA. And the force of gravity C, I should draw that. So I went and said I wasn't going to be careful about this, but I changed my mind. Okay. Now, additionally, on mass B, we have a force of gravity B and a normal force B, which I can't really draw it as long as it should be. And then there's friction. And again, since I believe the mass is probably going to move to the right, I want to draw the friction to the left. But if I do that and I get a weird, crazy answer, then I might have to change the friction. Maybe my guess is incorrect. In this case, I'm pretty sure I'm right. But in another problem, it may be not so evident. Okay, so now I have three masses. So I need to have Newton's second law for each mass. So sum of the forces on mass A equals ma times acceleration. We're going to use the trick. I'm going to say anything moving sort of up on the left and to the right on top and down on the right will be plus. And that allows me to give the same acceleration for all three. So I can just call this A. And then we have sum of the forces on B equals mb times acceleration B. And sum of the forces on C equals mc times AC. Let me pause. Other questions, because you guys are awfully quiet, and that makes you very passive learners, and much better for you if something doesn't make sense right now, and you can slow down and ask that question. Any questions? Haley.
Every time that we're doing like that acceleration trick, are we
Yes.
Are there any special instances where we cannot assume the acceleration is the same, or can we pretty much always assume?
So that can work when there's tension. If we have two things connected by a string, they're always going to have the same magnitude of the acceleration, unless if that's not really a string, it's a rubber band or something. We won't see that in this chapter, but toward the end of the semester, we'll have springs. And so when we get to things, it would not be true that the accelerations would have to be the same. For now, yes, it would always work that way. But the reason we do the trick is that the magnitudes of the accelerations have to be the same, but the directions are different. And so to avoid having one of them have a minus sign and the other has a plus sign, we do this trick, and that guarantees that their signs are all the same as well. Okay, good. Any other questions? Okay, so on mass A, I really only need to look at the y direction. I have TA and FGA equals m sub A times acceleration. And in terms of the signs of the forces, the TA is the one that goes with my blue arrow, so it gets a plus sign, and the FGA gets a minus sign. Okay? I'm just going to make a little barrier there. So for mass B, ideally, we're going to need the x and y direction. So in the x direction, we have TA and friction and TC. Looking at my blue arrow, the TC should get a plus sign, and the other two should both get signs. Now, if I work with this a little bit more, I have minus TA, and friction we can replace with mu times normal. And the fact that the normal appears is the reason why I need to go to the y direction. In the y direction, I have NB minus force of gravity B equals really just 0 because it doesn't accelerate. This tells me that NB is just equal to, I'm going to skip a step here because I'm hoping we're getting used enough to force of gravity just being mass times G. So my normal force is, again, just mass times G. And I can put that in here. So we have minus TA minus mu MBG plus TC equals MB times A. So mass B has more stuff going on it. And then mass C, again, is fairly simple. It just has TC and force of gravity C, and this is equal to MC times A. And again, using the blue arrow, we're going to get a plus sign for FGC because it's trying to bring the mass in the direction of the arrow, and the tension TC gets a minus sign. Okay, so what I have here are three equations with three unknowns. My equations, I'll quickly underline them in green. These are the three equations I'm talking about. Okay, so I'm not going to keep them underlined because I'm going to copy them and stack them on top of each other. So this equation I'm going to bring over here, and this one I will bring under there. And that is going to give me TA minus, let's make this MAG equals MA times acceleration. And the equation from mass C gives me a minus TC plus MC times G equals MC times A. So those are my equations. When I stack them up and add them, I can see that the TAs are going to cancel and the TCs cancel. So on the left, I'm going to get MCG minus MAG minus mu MBG. And on the left, I'm going to go ahead and factor that A out because we're getting better and better. And I see everything's going to have an A. It's starting to feel kind of formulaic. And then we can just solve for, move this to the next page. We can solve for A. Okay, so A is going to be, let's factor out a G from the left-hand side. So we have G times the quantity MC minus MA minus mu times MB all over MA plus MB plus MC. Okay, as I said, this is probably the hardest problem we have done to date because it's got three masses, so three sets of equations. But once we generate those equations, when we add them together, most of the stuff just, that we don't know cancels out, leaving us with only one unknown. So now we can solve. We have 9.8 times the quantity. Going back and looking at my masses, MC was 9, MB was 10, and MA was 6. So that is 9 minus 6 minus 0.2 times 10, where the 0.2, I believe, was my value from you. And then that's over 9 plus 6 plus 10. Okay, good. Now, if I get a positive number, everything is good. I am done. If I get a negative number, then it means I drew my friction in the wrong direction because this thing is moving the opposite way. So let's see what we get. So 0.392 meters per second squared. So because I got a positive number, that indicates that the direction of my blue arrow was correct. And if the direction of my blue arrow is correct, the direction of my friction was correct as well. So I'm done. That means I'm correct. If, on the other hand, I had gotten a negative number, that would mean either the friction was too big or maybe the mass on the other side was too big. And I would have to rework this with the friction pointing the other way. Now, the smart way to do that would be to just go into my equation, since I did it with equations, and just anywhere where I have a mu, change the sign of it. If I do that, it's like I did all the work over, but I don't have to actually do the work over. And then I test my number and see if it makes sense again. Fortunately, that probably only happens if I write the problem badly. Okay, if I write the problem and what I'm intending to happen. Okay, any questions about this problem? No? All right, that is basically it for my examples of Newton's laws. Let me kind of recap the key points here and what you should be looking for when you're studying. Okay, tomorrow we'll be moving on into chapter 6, which actually still involves Newton's laws, but it will not be on your content, and it's a special kind of different situation. So the keys here are we have all these problems. They can literally look like anything. We can have just a bunch of ropes hanging in some pattern, and we want to find the tension in the ropes. We could have something hanging from the ropes. We could have something on the back of a pickup truck while the pickup truck starts to move. We can have generally just gravity helping accelerate down a ramp. We can have things that are connected by strings or just, glued together. We have friction. We have pulleys. So it looks like there's a ton of different things going on, but that only looks that way until you've done a lot of practice, because what you should be looking for is how all of these problems are actually the same. I'll tell you, I know as a student, when I would be doing this work, I would start out looking at each problem and asking, how is this one different from the last problem? And I'd be looking for those changes. But what you really want is you want to be looking for how it's the same. This problem is the same as our other problems, because what's the procedure? We draw a picture, we draw in the forces, we write out Newton's second law for each mass and for each component if necessary, and then we add these equations and cancel stuff. So the details, whether there's friction or not friction, whether there's a pulley or not pulley, whether there's a ramp or not a ramp, those are, there's only so many variations there. We can have friction or no friction. We can have a pulley or no pulley. We can have a ramp or no ramp. And that's it. So you just need to learn, how do I deal with a ramp? How do I deal with a pulley? How do I deal with friction? And if you know those three things, then every problem within those possible variations is basically the same procedure. We either add in the friction if it's there, or we don't. If there's a ramp, we tilt our axes. If there's a pulley, we do the trick with the blue arrow. So it comes down now to you guys just practicing. Okay, and you should get to a point where you see a new problem that you've never before, and you just go, oh God, because it feels tedious. That's what you want. You want it to feel like the next problem is the same as the last problem. It's just, I have to do it because I'm a good student. I want to do all the problems, but I'm bored because I already know that I know how to do this. That's what you're looking for, because that's exactly how you want to feel on the contest. You want to look at the next problem and go, oh, okay, I'll do it. I want an A, but it's a waste of my time because it's easy. So you will not get there just from watching my lectures. You have to sit down and do the problems, because inevitably there's going to be something that you did that didn't click in the lecture, and you're not gonna get it until you do that problem at home and make mistakes. And then, as people are doing, set up times to meet with me and collaborate, and some help on the work you've been doing. Ask questions, and I think I think you have time to do that. Okay, so you can try to complete all of the homework tonight, if possible, and tomorrow, then you're asking me questions, or you're doing extra problems to test yourself, but you've kind of done all of the heavy lifting already. Okay, so does anyone have any questions remaining for me? Haley.
Oh, sorry, I just turned off my video on accident. So just to be clear, when we're filling stuff out, are the force of gravity and the normal force both equal to the mass times g?
Not necessarily. So the way we find the normal force is right here. Okay, so in this case, it is true that the normal force is the same as the force of gravity, but if it were, let's say this tension TC had been up at an angle. Okay, if that tension had been up at an angle, I would have TCY plus, and then this would have minus TCY. So they would not be the same in that case. So you cannot really rely on the normal force to be any particular thing.
Okay.
Instead, you should always solve for the normal force. And you solve it by summing the forces in the y direction. And if there's no acceleration in the y direction, which is normally what happens, then you find the normal force. Okay? But it is about, in a large fraction of your problems, it will turn out that normal force equals mg. Okay, good. Other questions? Emily. Emily, if you're talking, I can't hear you. Okay, I hear you typing. Mic isn't working. Okay, what's your question?
Okay, I think it's working now.
This
This is kind of unrelated, but for like the labs, for the corrections and stuff, when are those due? And for turning them in, do we just turn them in like on the same lab thing again, just a new PDF?
Yeah, so when you, the lab allows multiple attempts, so you just go back to the same lab and you just click it and it's going to allow you to submit again. And when you do, it shows me attempt number 1, attempt number 2, attempt number 3.
Okay,
So
when are those due?
You know, it's probably best if you get them in within about a week of when you get them back, but it's not really rigid. It's better for me if it's within a week because it helps me remember a little bit more what you did wrong. Also better for you because the longer it goes, you know, the more you forget that lab. But yeah, there's not a real solid deadline. I would say, you know, if you wait too long, if someone were to turn in a bunch of labs like on August 1st or something, like corrections, then there's a good chance there would still be lots of problems and there would no longer be time for a third round of corrections. So, you know, I would say the sooner the better, but certainly prioritize it lower than studying for the test and doing homework, and kind of fill in corrections whenever you have time.
Okay, thank you.
You're welcome. Okay, other questions? All right. So have a nice afternoon, and send me an email if you have questions. I'm not available much in the afternoon today, but I will be available later tonight if someone needs to meet and collaborate. Thanks a lot. See you guys later.